Here is a challenge. Write down a rule that identifies the number 7. Go on, actually try it. A horizontal line at the top and a diagonal going down and left. That is a reasonable start. Now here is a 7 with a bar through the middle. Here is one with a curled top. Here is one written by somebody in a hurry at an angle on a bad day. Every rule you write, somebody's handwriting breaks it. And yet, you recognized every single one instantly without being able to explain how. That is the problem neural networks were built to solve. Not writing better rules, but not writing the rules at all. So, let us build one, starting with the smallest possible piece. Take a picture of a digit and chop it into a grid of squares. Each square gets a number, how dark it is, from 0 for white up to 1 for black. That is your input. Not a picture anymore, just a long list of numbers. Now, the piece everything is made of. Picture a tiny decision maker that receives all those numbers at once. It does not treat them equally. Each input has a knob attached to it saying how much this particular number matters to me. Multiply each input by its knob, add all of that up, and you get a single total. If the total is strong enough, it passes a signal onward. If not, it stays quiet. That's it. That's the whole of one unit. Multiply, add, and speak up if the total is big enough. People call these neurons, borrowing loosely from the brain, but do not read too much into the name. It is arithmetic. Now put hundreds of those side by side, all looking at the same picture, but each with its own set of knobs, so each one reacts to something different. That's a layer. Then feed the output of that layer into another layer, and another. Each one is looking not at the picture, but at what the previous layer noticed. A grid of pixels feeding a column of units, feeding another column, feeding another, ending in 10 outputs labeled 0 to 9. And here is why the stacking matters. When you look at what these layers actually end up responding to, you see something rather beautiful. The first layer tends to react to the simplest things, tiny edges and dark patches. The next layer, looking at combinations of those, reacts to corners and curves. The layer after that responds to whole shapes, a loop, a long stroke, a junction. And at the end, one final layer takes all of that and votes on which digit it is. Nobody designed that arrangement. Nobody said, layer 1, you handle edges. It arranged itself, and we will get to how in a moment. 4 stacked panels showing what each layer responds to. Edges, then curves, then shapes, then a final panel reading, it is a 7. So now the honest state of our machine. We have a structure with an enormous number of knobs, and at the start, every one of them is set to a random position. You show it a 7, and it confidently announces that it is a 2. It is not broken, it simply has no idea, because random knobs produce random answers. So pause the video and think about the actual problem. You have millions of knobs, you know the answer should have been 7, and the machine said 2. How on earth do you work out which knobs to turn and in which direction? A vast wall of randomly positioned knobs with a confused figure holding one hand up, labeled, "Which ones do I turn?" Here is the answer, and it is the entire trick of the field. You do not guess, you measure. First, measure how wrong the answer was as a single number. Then, and this is the clever part, you can work backwards through the machine and calculate for every single knob whether turning it up or down would have made that number smaller. Not by trial and error, by calculation. So you nudge every knob a tiny amount in the direction that would have helped, not a big turn, a whisper. Then you show it another example and do it again and again. Millions of times. An error measurement flowing backwards through the layers, with every knob receiving a small arrow showing which way to turn, labeled measure, then nudge. No single adjustment achieves anything, but run it for long enough and the knobs drift into an arrangement where the machine is right far more often than it is wrong. And if that pattern feels familiar from our series on large language models, it should. It is the same idea at a very different scale. Now, sit with what has actually happened here, because it is genuinely strange. Nobody ever told this machine what a 7 looks like. Nobody wrote a single rule about lines or angles or curves. All anybody did was show it examples, measure how wrong it was, and nudge. The rules for recognizing a 7 do exist inside it now, but they are not written anywhere you could read. They are spread across millions of knob positions, and nobody, including the people who built it, can point at the part that knows. A machine correctly identifying a 7, with a magnifying glass searching inside it and finding only a sea of numbers labeled, "The rule is in here somewhere." And that leads straight to the honest part, which matters more than anything else in this video. This machine does not understand what a 7 is. It has no concept of numbers or counting or writing. What it has is an extremely well-tuned reaction to the kinds of images it was shown. Which means when you hand it something unlike anything in its training, it does not become uncertain and say so. It confidently gives you an answer, because giving answers is the only thing it can do. It also inherits whatever was in its examples. Show it only neat handwriting, and it will fail on messy handwriting. Show it examples that were unfair in some way, and it will reproduce that unfairness precisely, without anybody having intended it. The machine has no opinions. It only has the residue of what it was shown. A machine confidently labeling a scribble as a 7 with no hesitation beside a stack of training examples it never saw, labeled, "It only knows what it was shown." So here is the big picture. A neural network is a huge pile of very simple arithmetic. Each unit multiplies its inputs by knobs, adds them up, and speaks if the total is strong enough. Stack those into layers, and each layer builds on what the last one noticed. Start the knobs at random, measure how wrong the output is, calculate which way each knob should move, and nudge. Repeat until it is usually right. That is the whole thing. Every image recognizer, every voice assistant, and every language model you have ever used is that idea made enormous. A simple summary strip reading, multiply and add, then stack in layers, then measure the error, then nudge the knobs. And the reason it took decades to work was never the idea. It was that nudging millions of knobs across millions of examples needs an astonishing amount of arithmetic, and the machines to do it did not exist yet. The concept was waiting. The hardware was not.